Hello and welcome to the new episode of Inside XRF. My name is Konstantin Brentgens and I'll be your host today. And today's topic is one of our first-hand experience of the applications we are running. And the topic today is glass sets for short-lived samples, or as we like to call them, transfer sets. Give me a second, let me just get this spotlight back. Okay, so now I've got my red dot again. So yeah, let's get into the presentation. As always, feel free to write any questions in the Q&A section of the presentation, and we'll try to address some at the end if there is time. Otherwise, we will get back to you by email to answer the questions that arise during the presentation. So to get started for this, I would like to make a little excursus just as a kind of preparation, because that will help us understand later. When it comes to XRF, one important thing we need to understand that basically the XRF as a measurement is just counting atoms. So the equipment itself measures a certain energy in counts per second, and these specific energies correspond to an element in the periodic table. So as an example, we have iron down here, and we have the K alpha and K beta lines. So basically what the spectrometer is doing for us is simply counting the amount of atoms inside a sample that we measure. And when we are doing a calibration, we then we invest some time and effort in order to convert this measures intensity, the count rate of our atoms, into a more usable unit, like, for example, mass percent, or ppm, or microgram per milliliter, or per square millimeter. So we're taking the signal from the measurement and we're transferring it into a unit or a results. And that whole process generally is called calibration. So we use standards and we generate these so-called calibration curves. I'm pretty sure most of you are familiar with that. I just wanted to kind of repeat this because that will help us later to understand how the transfer sets work. So also, let's just, we have a little excursion here into norms and standards. This is a German norm on how to do certain samples, and I did not bother to translate it into English because the summary here is here. When it comes to calibration, usually the first rule that is applied is that the standard samples that we use to establish this calibration curve and the unknown samples that we analyze later, they are treated the same way throughout the entire process. And this is something that we will not do with our transfer sets, and I'll explain in a bit more detail why not and what will be the difference. But generally speaking, classical calibration means everything is treated the same way, from the standard sets that we use for calibration to the samples that we later analyze. So to give you like a schematic or a roadmap on how to do a classical calibration, it is we start with the standard samples, and the standard samples are basically the same as the unknowns we measure later, be it a powder, a liquid, or some solid samples. We then do preparation. Again, in preparation, we keep all parameters the same for the standards and the unknown samples later. We then have the measurement part, and all of this leads to a calibration. So that is your classical approach to develop a method, an application. When we're working with these transfer sets, we do a different approach. In Generally speaking, the transferred standards are always fused beads. And so our samples are basically ready, our standard samples are basically ready. We can proceed with the measurement and we can go directly into calibration. So the big difference is here is basically the sample prep kind of falls off. So it is, as you can see, a quicker method to begin with. And the question is now, what are these standards in more details? And I'll come to that in a second. But before we talk about more detailed using an example on how to build one of these transfer sets, I just want to kind of make a little excursion into the standardless softwares, because everything I've been saying until now is basically a good description for standardless softwares as well. Standardless or semi-quantitative methods, there is various different ones out there depending on your spectrometer, but usually each spectrometer comes with one of these packages. And the idea is that standard samples or standardless softwares, they work with all samples and all preparations. Basically, when you're running a measurement of your unknown sample with a standardless software, what you input is the details of that sample. You tell the software package, this is a fused bead, this is a pressed pellet. You give him the amount of chemicals and additives used. And the software then, the standardless software, takes this information to make an analysis of that sample with all these details. So generally speaking, a standardless software is doing the same thing as our standard sets, as you will see later, but it solves the challenges that arise here mathematically. So you give the information, the standardless software calculates, and then it gives you a results. And for each measurement, for each sample, you might have to input different details of that actual sample. The question is always in the end, is the accuracy sufficient? One of the downsides of standardless software in general is that it is not very accurate. It's basically a very wide program that can work with all different samples, but the accuracy may not be sufficient. A transfer set actually allows you to achieve comparable accuracy to a pattern method. So basically what you have is a method that you want to copy with a transfer set, and the accuracy stays the same. So with that in mind, let's go into the detail of a standard set. So as an example to kind of guide you through the process, because it's a multiple step process, we took an example, and in this case, it's an oil calibration. So the samples we are analyzing are liquid oils, and we are looking for wear and tear metals, so to say. So classical approach would be, we have our oil samples, we have the preparation, analysis, calibration, and results. We'll talk about each point in a bit more detail. So if we're looking at the oil calibration samples, there is something to keep in mind here, which in the end will also explain to us why we want to do a transfer set to begin with. So when you're looking at oil standards, there is a lot of different standards available. They're usually single element standards, and they can be bought by demand. So there is a lot of companies out there that will just offer you the element and the range you want as one standard, and yeah, there's a fixed cost to it. So they are produced on demand, but they also have an expiring date. So this is one of the problems with these samples. You can only use them for a specific period of time. because otherwise you basically lose the validity of your certificate. So the ones, for example, that we use, they are stable after 1 year. They are stable for 1 year after opening. So there is a time factor involved here. And when we're looking at the calibration, so we're going to sample prep now. We have our sample. We then for a calibration, like I said, we have multiple single element standards. We make a dilution, or if we use the standard as is, we simply mix them before measurement. Usually what we do is we take the high concentration point and we dilute it down to get a calibration. So as an example, we might have a 1,000 ppm as a standard, and we go down to like 700, 500, 300, 100, 0. So we use one standard that we bought to make a dilution, and we use up that material in the process. We put them in a sample cup, obviously. We then fill a certain amount, and we measure the sample cup in helium. There is a few problems kind of attached to that. Simply or mainly speaking, these measurements take quite a lot of time. I'll come back to that in a bit. So to kind of compare it with the transfer set, I think that's a better idea. So for analyzers wife, this is actually taken from one of our method downstairs. To give you an idea, this one oil method that we are running, it has like 10-ish analytes in general, but we have over 200 standards. The reason being, these are all single elements diluted down from 1 or 2 high concentration standards. These are all measured in helium, and yeah, the measurement per sample can be between 5 and 15 minutes. So this can be quite a lot of effort when it comes to the calibration part. So yeah, this is one of the curve. This is calcium here, for example. And as you can see, for calcium, we use 30 out of our 200 available standards. So the whole set is quite voluminous, so let's say. It's a lot of standard materials and a lot of work. In fact, when I was doing this took me 2 weeks in total to get the standard prepared, measured, and do the calibration. And by the end of these 2 weeks, I had almost used up most of the standards that were available. Keep in mind, these are like 100 milliliter bottles that you buy. And so if you want to do some recalibration or even some testing on a regularly basis, which happens here in our lab, and it's always kind of a problem because every 6 months we have to revalidate this method, for example. And the first question is always, is my standard still, is it expired or is it still okay? Because if it's expired, I have to replace it first before I can do the revalidation. So something to keep in mind in terms of the effort the effort that goes into one of these applications. In terms of, as an example, the liquid application, this is a lot of time and preparation that goes into that. So if we now want to have this one transferred to another laboratory, for example, this is where a transfer set comes in handy. So once we have done this one time and we have the problem, or we have the method established based on the classical model by using the standard the same way as the unknown samples later, we can then analyze a transfer set or create a transfer set. So the idea is that with the application that we have developed, we will take some glass samples and we will analyze them. So we are taking something different from the actual method. We are measuring fused bead or glass samples in an oil method, and that allows us to freeze this application with solid samples that we can store very easily, and it makes the method transferable to a different spectrometer, for example, or a different laboratory very easy, because we don't have to do all the effort I described before with handling the liquids. So we do that one time, we then freeze the application using synthetical samples or glass samples, and we can use those to transfer to a different place or spectrometer with much less effort and a lot easier to store. So the whole process becomes something like this. We do the application once, we then make the analysis of our transfer set, and we do the calibration then, and we come back to the same results. So the whole idea behind these transfer set in generals, these transfer sets in general, is to avoid effort in sample prep and measurement and handling, and make it easier to transfer them, or to have a physical backup of our method in ways of samples. If we compare the preparation, we made this little table to kind of show the details of both. So in our example, if we look at a liquid sample in a sample cup, in terms of equipment, there is nothing we need. We just take the sample cup, we fill the liquids, and we measure it. The sample cups themselves are one use only. So after the measurement, we throw the sample cup away. If we wanted to do a repeat measurements, you could refill the content, the liquid, into a new cup, but we never use sample cups twice, and we don't recommend doing that at all. It is very quick in terms of measurement, or well, it's more like preparation here. The measurement of the method is kind of a fixed time that we have to invest, and it depends heavily on the amount of isolates and so on. But doing a sample cup and then just preparing it for measurement, it takes less than 5 minutes. So you just assemble, you fill, and you go to the spectrometer. I usually recommend to have like a sort of a safety period just to see that it doesn't spill. So you leave it there for a minute or two to make sure it's stable, and then you measure. Measurement, of course, would need to be done in helium atmosphere to prevent it from evaporating. Air would also be an option for some application, but usually helium is the go-to. The accuracy is very high, since we have an ideal sample, and yeah, the durability of the preparation is one measurement, and then basically throw away. Or as I mentioned before, if we want to do repeats, you can refill the liquid into the next cup and do it again. If we compare this with the fused bead now, what we want to use in our transfer set, we do need more equipment for that. We need first of all, of course, we need the capability to make fused beads. So least of all, we need some platinum dishes and a muffle furnace to do it manually. More modern and well, how to say, like the more reproducible approach for this. The problem with manual fusion, it's not really repeatable. So we have all these different automatic fusion machines. They come in gas-driven and electrical-driven, which basically is a muffle furnace again. But still, we then need one of these automatic machines, and still we need the platinum to do it. As consumables, we have the flux, the tetraborate that makes the glass, and the consumables for the equipment, gas or electricity, depending on the machine you are using. And the effort it takes to make one sample is around about 30 minutes minimum, because it's balancing, mixing, and then doing the fusion sample, which in total ends up to around about 30 minutes per sample. You can do multiple samples in that 30 minutes, but still, it's kind of an idea how long it takes compared to the sample cups. So measurement, since fused beads is a solid sample, you can basically measure them in all atmospheres you like. For our transfer sets, we'll of course use helium here to simulate the oil again. But I think that is clear. If you want to do the transfer, you'll analyze in the same atmosphere. You just use the same measurement program and the same environment, basically. Accuracy of the measurement is comparable. Again, a fused bead done well is also a very nice homogeneous sample, so no problems there. And the key aspect now on why you want to do this actually is that fused beads can be stored for quite a long time. It's difficult to give exact numbers here depending on recipe and chemical composition. This can vary from like half a year up to many years in total. And the storage condition play a huge role here. If you leave them out in the open, they will degrade faster. But if you put them in a desiccator, for example, they can last for years. So the whole idea behind the transfer set in this example and many others as well is we invest a bit of time to reduce the effort later, basically. You see, the measurement in a sample prep is quick and easy, but not durable. And you have to redo it every time. So it gets like, it's a small effort, but you do it a lot of times, basically. And if you can use a backup or can freeze a method in a transfer set, you only have to basically do that once. So the preparation takes more time, but the preparation is then stable, and that's what makes the whole freezing possible. So you're probably familiar with this one already. We used that in a lot of other webinars where we talked about diffusion in general. But yeah, the whole idea is you take the sample, you mix it with tetraborate, you put this mixture into a platinum crucible, you do your fusion, manual or with a fusion machine, and the result is a fused bead. So now the question for you is probably, why does not everybody do this? And yeah, that's a very good question. Why is this not the standard approach for any method or for any application that requires a bit of effort in handling the samples? And yeah, the answer here is it's not that easy in practice in the end. In order to make the glass sample, we have to understand we are using completely different samples to our metrics. And so we have to consider a lot of steps when producing this. The first thing is, when we're doing this, we're usually using pure chemicals or primary oxides, and we have to make sure that we have stable oxides available in order to do that. In the end, the oxidization steps plays a role here. Remember in the beginning, I said we are only counting atoms. So the oxygen attached to these atoms, which make up the oxidation state, don't really matter, but they matter for balancing. And in the end, what we want to do is we want the fused beads to represent or to simulate the oil sample in our example. So that's where the difficult designing comes in. Also, we have to keep in mind that the analyte form that we are looking at, for example, in our oil application, we might be looking at Fe as a metal, but in a fused bead, this would be Fe2O3, like an oxide. So we have to kind of have the conversions between these oxidization states, and we have to think about that up front. And also, a lot of these elements, we have to think about the hazardous potential of the pure chemicals as well. So there is a lot of planning and designing involved here. And when it comes to designing of these calibration sets for transfer, there is a few key questions to keep in mind here. The first one would be, how many points do you want for a curve? Obviously speaking, when we look back, or if we remember from my oil example, there was the oil method had like 200 plus standards because it was 10 elements and 20 standards per element, all single elements. So if we want to do this with a fused bead transfer set, obviously we don't want 200. We want to go down to maybe like 20 to have like a good evaluation. And we can make multi-element standards here. So the reason to do a single element is mostly a practical thing, because it's kind of hard to mix different standards. So it's easier to make just like a dilution series. But of course, when we're talking about a transfer set, we want to keep the total amount of standards smaller and have them all work for multiple analytes, basically. The composition here, there is some limitations. Also, we have to think about what corrections do we, like inter-element corrections, do we want to implement? So we have to look at the source application and copy basically the settings from there, or the plan for inter-element effects. And based on that, we need to design a standard set that makes sense. And then the question for validation or validity sample is also, do we want like an extra one to have a control sample in the future? So usually, just to kind of give this as a schematic, I've been talking a lot now, so we want to just put it in a sort of graphics. So the way it works is we have an established calibration. In our example, we're talking about an oil standard. So we have concentration versus intensity, and our blue little points here, these are our calibration standards. The green ones are there for validation later, which is classic again. You do a calibration, you validate with some samples which are not part of your set. And so the idea for us is, by doing some measurements, we introduce basically fused beads into this, or we make fused beads and give them concentration results on this curve, basically. So we now have a curve made out of the oil standards in liquid form, and our fused bead standards that we later want to use to transfer it somewhere else. And then we just simply get rid of the oil standards. So we now take the fused bead, we go to a different spectrometer to start with, and we make the calibration again, but we are only using the fused beads now. And after we've done that, we validate it again using oil samples. So we basically make an application, we then back up or freeze it with different samples, fused beads, and so we can easily transfer it on a different machine. And of course, what we want to achieve is the same results in the end. Now that we use unknown samples, we want to have the same results as done with the oil method. Yeah, that's the whole principle. We'll round the whole presentation up with a few ideas, with a few examples to give you some ideas where this makes sense. So one of the examples we are using here in FLUXANA laboratory is filter paper. In this case, it's silica on paper. We are analyzing these little papers between thin films, and the reason we decided to do this as a transfer set is generally because there is no standards available on the market. This is a common theme. You'll see that in the other example as well. So what we had here is we had some real samples and we analyzed them as a referent method. So we sent them to a different lab and got the results, and we used that one then as a calibration sample. So in the end, we only had these few samples available that we have basically cross-certified, and we couldn't buy any others, and we could also not reproduce them because they were only part of the batch. So what we used here is a transfer set as a backup for the method later. We used I call it freezing before. We used the fused bead sample to freeze this method, and it's basically a backup. So whenever we need to install this on a different machine, we have it available without having to go through the whole effort of making new standards. You could also apply this to any sort of filter paper. So I've seen those applications in the field where people would analyze filter from a systems, and the same applies here. There is no standards and they're not replaceable. So once you have an application, you want to have a kind of backup, and you can use a transfer set as a hardware backup. Another example from the lab is animal feed. In animal feed, we are mainly looking at pollutants, and these can be detected very well with X-rays, but the problem of the sample is that it's not homogeneous. So in order to, you can probably see from the pressed pellet here, just from the structure, it's like it has a lot of particle effects and it's not homogeneous. So in order to have a good calibration, you usually go for multiple preparations per standard. And again, there is really no CRMs available on the market. So we have a lot of effort again into going into one method, and if you want to transfer that on a different machine, fused bead or a transfer set is a good idea. Another example is general liquids from electroplating or electrolysis. This was a sort of a project that we did. The main problem here, this is liquid analyzers in general, but the liquids are highly hazardous. So handling them or transporting them is basically out of the question. You can only do this on site at the plant, and there is no real way to transfer it after then, because you can't just fill this into a bottle and go somewhere else. It's all like extremely dangerous. So again, a transfer set is a good option here. Generally speaking, when is this method of a transfer set useful? It is generally useful for inhomogeneous samples or samples that are difficult to handle as a material. So liquids or like I said, the baths before. And the challenge is always to design a set that makes it easy. So this requires quite a lot of testing and know-how. And so in the end, it's always a question of cost benefit. Does it make sense to go for a classical calibration, treating the standards the same as your unknown? Or does it make sense if you want to, for example, spread it across multiple laboratories of a group? Does it make sense to have one set and transfer it to all these places? Yeah, that's about it. Thank you very much for your attention. I see there are some questions. We'll get to those in the emails. And yeah, have a nice day, and I'll see you next time then. Goodbye.